recording this, but it's from the H. Say again?
Seaweed.
Seaweed. It is very good. Right, then to the other half of the class. You have a class later, no? Yes. At 4.
No, at 3.
At 3?
Yes.
At 3. Okay. Then, well, I was talking to you yesterday about this Markov process, the random walk, and I asked if someone could solve this problem or understand why I put that formula. So, if some of you knows the answer, please tell me. If not,
I don't know the answer.
someone?
Yes.
You can come to the blackboard and explain to your students.
Just the equality, right?
Ah, yes. Yes. Okay. Okay. So I won't record if you don't want. Okay. You can find it. There's no. Okay.
The light? No, switch it on. The middle switch. So we want to show that the probability that you are at point X at time T, we said it's equal to the 1/2 raised to the number of times you go to the right times 1/2 the number of times you go to the left minus taken n plus. And we want to show that this is equal to this expression over 2 factorial, right? To show that if you want to get the probability of having the position x at time t is also just dependent to the t and x. So first we need to know 2 things. So if you see the sum of the steps you go to the right and to the left is just equal to time. And if you get the difference, okay, this is actually equal to x. It's just the displacement.
Okay, so it does n plus jump to the right, n minus to the left. The difference is x.
It's x. Okay, so we use this to show that equality. So first, we can combine this to have 1/2 raised to the sum of n plus and n minus. So you have 1/2 raised to t, which is the first expression there, which is 2 raised to negative t. And this last here is can be written as t factorial over t minus n plus factorial and then n plus factorial.
How do you call this?
Is the binomial coefficient.
Binomial coefficient.
Okay.
You can, some places you can call it in a simpler way. It is t chooses n.
Yeah. The combination.
You see this t or combinatorial number, but this is t chooses n. Okay, it's a way of saying the same thing.
Okay, so what I did is to start from
That's
here.
That's it.
T plus x over 2 is actually.
No, actually, you are here at this point.
Yeah.
So you should reach here.
Yes, but
Okay.
I didn't.
Sure.
So because if you observe t plus x over 2 is actually n plus. So this is this term.
Yes.
Okay, and t minus x over 2 is t minus n. Yeah, t minus n plus. N plus. Which is this. N minus.
Yes.
Because it's.
Sure.
Yeah.
Okay, so
you have the over.
this is correct. But now I'm in question because
Okay.
you showed this part, this
Yes,
equal to
this
this.
is what it is.
Fine.
Okay.
It's clear, no? Yeah. But now my question is this part. Why did I write this? What is the logic behind?
Okay. So
Yeah, this is good. With the drawing, it's
Yeah.
useful.
so if you start from say at point 0, and x is the position of the say particle from the origin, so x. So this two here, because there's a 1/2 probability that you go to the right, and then 1/2 probability that you go to the left.
Yes.
And so to go from point 0 to x, there is a certain number of n plus and n minus.
Yeah. Sure.
Right?
Yeah.
So since the steps are independent, so you just have the probability 1/2 times the number of times that you go to the right.
Exactly. In every step, you have
Half
to
probability.
go right and left.
Yeah.
So the sequence, any sequence you look, it will have probability. In the sequence of jumps, we have the same probability.
Yes.
Jump, if you jump right, it's the same as jumping left.
Yeah.
Okay, this is what comes here.
Here in this part.
Yeah.
And this part, it is the number of ways that you choose n plus, or it's the number of ways that you choose how many. Say for example, you go from 0 to 3. 1, 2, 3. So you know that you need if x is equal to 3 and t is equal to, say for example, 4. Okay, so one way is you at time 1 you go here, here.
No.
You
go back and
You go back and then you
Yeah.
No.
Time is equal to.
No, this doesn't work.
This does not work.
Yeah, no.
Forward, backward. This will work.
Forward,
Yes.
forward,
Yes.
and then forward.
Yes.
But
There is another.
there's
This is one
another.
part.
This is just one way.
And that part is it has this probability of jumps.
Yes.
But you can have the same type of jumps, but
Yeah.
ordered in a different way.
Yeah.
Okay?
So that's it.
And that's what brings this number.
Yes.
Okay, thank you. This is good. Let me start the recording. So today is lecture 7. It was already initiated with a nice exercise solved by your colleague, where we showed the probability in a random walk to be in x times t. And this is the correct solution. And as your colleague was saying, you can reach, let's say, x equals 3 in 4 steps by doing a forward, then forward, forward step. But you could also do forward, and backward, forward. Okay. Each of these have a jump probability. The sequence of the jumps is this probability. All of them have the same probability for the sequence of the jumps. So how? If we say probability to be at x20 is we are summing over different sequence of jumps. Okay, jump sequence. This is a very not very precise way to write it. Okay, probability for the jump sequence, which is all the same, but then you have to count how many of these happen. How many of these are available? So this is what we are counting with this number, the combinatorial number. The combinatorial number is equivalent to some different quantities, because this will be a quantity that we get in a one. So the main point is the following: that let me try to illustrate with the tree. I think the tree is probably the easiest. So if I write a tree, let's say like to know, for example, for it to be at 3 at time 4, at time 0, 1, 2, 3, and 4. Then we do this. So one option is forward. Okay, this is now time and this is x. One option is forward, then forward, then back. Okay. Backward and then forward. Okay. No, sorry. Forward, forward, backward, forward. And we are in 0, 1. We are in 2, eh? This is time 1, time 2, time 3, time 4. You need to be at 3, time 4. This is 0, 1, 2, 3. Okay, so forward, forward, 2.
It's time 4 actually.
It is time for.
Because we have 4 steps.
Yeah.
Each step is 1 time.
Four steps.
Yeah.
Okay, 3, and then the fourth step will bring me to 4, to 3. Okay. Okay, this is sorry. Sorry, I'm doing a mess. This is x, and this is t. Okay, so time 4, I want to be in 3. This is time 4, and I am in 3. Okay, this is one path.
Actually, is time
This is time 0.
0?
1, 2, 3, and 4.
X, okay.
And we want to count probability to be at x equals 3, at time equals 4. This is the one we want. So that x equals 3 is here, time equals 4 is here. You want to count how many trajectories hit this point.
When you went from time 3 to 4,
Can you speak louder because I can't?
when you went from time 3 to time t equals 4, you went from x1 to x2. So that's
Wait. Let me do things properly. So first I jump forward. Now, in the next one, I jump also forward.
I think the difference should always be.
The next, I jump backward. And the next, forward. Something is wrong.
Yeah.
That is wrong, sorry. X, that won't happen. X3 and 0
I'm totally lost now. So, forward. Forward. Backward. And forward. Now I'm time 4. X2.
I think from the equation, this is not possible.
Not possible.
Yeah, because if you t minus x, you have 1/2 factorial.
1/2 factorial.
So, my example is actually wrong.
It's wrong. This example is wrong. So how can we reach here? This is a good question. We could reach, for example, like this.
Yeah.
Now,
No,
we cannot.
that's why it's here. That probability is.
Okay, so we can check maybe here.
You can pick a path.
Okay, we want to be time 4 in x equals 3. So how can we do this? We could do one step forward, another step forward, another step forward, another step forward. You don't make it. You don't make it. So there is no way. There's no way. And this is
There
actually
should be 4 ways.
why
From here.
this is not possible.
4 choose 3 is 4.
I think the difference between them should be.
T minus
Should be a
x.
restriction.
There needs to be a restriction.
There needs to be a
The
restriction.
rest of
There needs to be a restriction. So T minus x, what is T minus x here?
1.5
1.
factorial.
1.5 factorial. What is 1.5 factorial?
Square of pi over u.
Square of pi. There is here a problem, you see? The formula is telling to you. So the main thing you learn from here is that not all positions are available at time t. For example, in the first jump, you cannot reach 2, for example. You cannot. And this is given by the formula. But let's take a simpler case. So this is 0. That's the main point. This is 0. Let's take a simpler case, which is, for example, the probability to be at time 3 in 1, for example. Okay, let's see. So we go forward, we go forward, and we go backward. This is fine. You can also first go backward, and forward, and forward. Okay,
Forward, backward, forward.
it was forward, forward, backward, backward, forward, forward, and
Forward.
forward, backward,
Forward.
backward, forward. There are 3. We counted 3. And the 3 is the ones that come from here. Okay, because we do time, we said t is equal to 3. So t divided by n plus will be 3 chooses 2. Okay, n plus, yes, n plus is the number of steps forward, so we said it's 2. Sorry, give me a second. T divided by n plus, yes, and this will be
3 factorial over 2 factorial.
oh yeah, over 2 factorial.
Yes.
3 times 2 times 1 divided by 2 times 1. You see? This formula, this combinatorial number is telling you how many ways you can choose n plus options in a length of size t. Okay?
Then it should work with that too, because according to the combinatorial factor, there should be 4 ways of doing that.
Yeah.
Yes. 4 factorial divided by 3 factorial into 1 factorial is 4.
Yes, and you have 3 factorial.
I'm sorry?
Which you are talking about the last example, x equal 1, t equal 2.
No, this one will be fine. This will be
4.
okay. This will be
Technically, that should be
1/2 n plus, well, n plus plus n minus will be t, so 1/2 to the power 3 times t. So the probability of this will be 3 divided by 2 to the 3, which is 3 divided by 8. Fine. Okay. So this is the way one can work before. Make sense to you?
My question is, why didn't that work?
Ah,
Yeah, that is what I'm saying. Why
it
didn't
won't work because it won't solve the system of equation we have. N plus plus n minus equal t, and the plus minus n minus equal x.
It won't.
If you try to solve the system, you won't find integral in n.
That's the point. That's the point. So you want solve this equation. But it's very important for you to see that the random walk is not the discrete random walk. There are some positions that are unavailable. When it's continuous, we can reach everywhere. Okay, this is a particular case. There is another way. So, in principle, okay, here I was clever enough, or you were clever enough, and we all were clever enough to recognize this. But there should be a way of getting this quantity mathematically. And the idea is that there is an equation satisfied with this. So there is something called master equation that I will introduce later in the course. Master equation, which is basically an equation describing the evolution of this object. So here I can tell you, we can at least get an idea about it in the following way. So when you are in Bxt, let's say I would like to know what is Bx at t plus 1. Okay, or no, let's say I want to know Bx. So the main point is here, you can see this as a probability flow. There is probability flowing between different times and positions. So to reach Bxt, if you think about it, you can only reach from 2 places. You can come from here, and you come from here. Nothing else than that. So when you are here, you have 2 possibilities, either go left or go right. So you can write pxt as it has two positive contributions. You can enter from p x minus 1, p minus 1 with probability 1/2. We could write like this, 1/2 plus the other contribution plus 1/2 e of x plus 1 e minus 1. This is the influx of probability to xt. You all follow?
Yes.
And then there's also escape. So you will also escape from pxt. Okay, this is the gain, and then there's the loss. Minus. Actually, this is like this. So pxt, actually from time t, you can gain from t minus 1. Okay, that's it. Then, yeah, I think this is the point. Then you may also lose probability. No, I think the point is as well, you lose probability from pxt, but you lose it in the next step. So this is a, say, master equation for the system as a function of time. So if you take this equation, you will see that this equation obeys, this pxt obeys this equation.
But the master equation, the P is just the canonical delta, no?
Yes, yes. Later I will give you a more general expression for the master equation where you will see all these terms. Okay, more general. This I'm solving now a model, but I will give you what is a formula for all Markov process. This is just for one, this simple case. So you will gain probability for these two sides. Yes.
The n plus is there one step to right?
Yes. N plus, which means that right, is the total number of steps to the right. In time t. N minus is the total number of steps to the left in time t. Okay. So in time t there are t steps.
It's a total possible way to maximum of.
No. This is a random variable that depends on the trajectory.
So
for example, this trajectory.
we have three ways.
Wait. This trajectory is right, left. For this trajectory, n plus equals 2 and n minus equals 1. Okay?
So now, when we calculate t of n plus, it gives us 3. And what this 3 means?
Wait. 3 means that you can hit. Oh, my God. You can hit this point with 3 paths. This was one. Another one is, so this was forward, backward. But you can also do backward, forward. This one has also backward only 1, forward 2. But this is another path. Okay. Blue color, white color, 2 paths.
And now if we calculate that with the blue path, the answer will be the same.
Okay, yes, but in order to know the probability to be here, you need to sum all the paths. There are many paths that arrive here. That's the number 3.
Okay.
1, 2, and the third, I have to take a color. There's a third path. The formula should be consistent with the drawing. The third path is, it has 2 forward, 1 backward, but I can do it like this: forward, backward, forward. This is the third part. Okay. There are three ways to reach xt in this example.
Yeah.
Each of these have a probability for transitions. Each of these has 1/2 to the power 3 to have this sequence, and plus. Okay. But another thing is in which order you put them. There are three different orders that are compatible, which is this. So we are doing this, plus this. There are three ways. You are summing the probabilities. And this equals 1/2 to the power 3 times 3, which is 3 divided by 8. So all these combinatorics that we are doing here by eye is given to us by this formula. Okay. Right?
I was thinking that we calculated the combinatory of t and n plus with the 3 and 2. Yeah. If we choose the trajectory, the red one, the number of steps to the right will be again becomes 2 or 1.
No, here is 1 to the right, 1 to the right, 2 as well.
2. Okay, that is okay. Yeah.
Same. All right, is it clear?
Okay, thank you.
Very good. So this was,
Can this be approximated to the continuous random walk?
you can approximate, but then it's a different process.
Oh.
In the sense
Is that a
that
Markov process?
it will be Markov, and this is what I will explain you now.
Okay.
So now I will give you an insight on another example that is a diffusion, which is the continuum limit of the process that I'm showing you here. So this is actually called diffusion or also Wiener process. Of course, I showed here discrete time, discrete space, no bias. In general, random walks have bias. So things will have.
Bias as in drift?
Bias is a drift, so it means it's not 1/2, 1/2, but maybe 2/3, 1/3, or 9/10, 1/10, and so on. This is a second example. Sorry?
Yeah.
Second example of Markov process is the Wiener process. Wiener process, which will appear a lot in the course, also called the Brownian diffusion. In which x and t are continuous. This is defined as follows. So again, we will say x at time 0 is 0, and it evolves following an equation that I'll give it later in the course in detail, but it's this one. X dot, the velocity, is the square root of 2d times noise. And this, we call it Gaussian white noise, which, let's say, explanation, detailed explanation will come later. Gaussian white. It's an uncorrelated process. The process is defined as follows. So, as I said, for Markov process, you need two things: the distribution at time t and the transition probability. So first, I give you the distribution at time 0, which is delta x. What does delta x mean? It means a delta function, so it's only at 0. What else do I give you is the transition probability. This given this. We know at time t1 you are in x1. What is the probability that you go time t2? For a diffusion, this is a Gaussian type is 1 divided by square root of 4 pi d times exponential square divided by 4d d2 minus d1. This it means that there is a Gaussian distribution. The Gaussian is usually called propagator. Propagator means it's a conditional probability. Okay, so what is important is that the one-time distribution. So, for example, if you say, let's take here x1 equals to 0 and t1 equals to 0. Then I will call t2, I will call it t. So I tell you this, you should know how to calculate pxt. Pxt is taking this and putting this equal to 0, is equal to 0, and so. Okay? So what you get when you do this replacement here is the following. You get pxt given 0. 0 is exponential of minus x squared dt divided by square root of 4 pi dt. This is the way Gaussian distribution. So I will do a bracket here. It doesn't mean there's a multiplication, but remember, reminder, what is a Gaussian distribution? Let's say we have a normal distribution with mean mu and standard deviation sigma. You know this, no? What is the distribution? This. Well, there is an exponential first, minus x minus mu square divided by
Sigma square.
2 sigma square divided by 2 pi sigma square. Good. This is a Gaussian distribution. Okay. Gaussian distribution. This is also Gaussian, you see it. You see it. The Gaussian with mean 0. And variance, well, if the mean is 0, the second moment is the variance. And this is equal to, if you compare the formulas, you see, it's 2 dt, no? Which is what we talked about before. 2 dt. So the variance is increasing with time, linearly with time. In this process, you have the distribution. And I'm saying for this particular case, at time 0, this is x, this is p of x and t. At time 0, you have a delta, this is p x 0. And as time goes, the variance is increasing. So you have a Gaussian that is spreading. So then you will have something like this. And then you will have something like this. So when time goes, this is p t prime, and this p x t prime prime greater than t prime. We have a diffusion, means if you put many particles in one location and let them go, they will spread. On average, there will be the average of the position of the particles will be 0, which is this, and they will spread. They will diffuse. That's what the formula says. So with this, I tell you, with this you can calculate the probability of any trajectory in this Brownian dynamics, right? So I said, if you want to know now from here, you want to know what is p x1 t1, x2 t2, t3. This will be easy because here you will need t1. Then, okay, this depends. Then there will be this propagator. There will be a Gaussian propagator. X2 minus x1 squared. 4d t2 minus t1 divided by the square root. And then there will be another Gaussian with x3 minus x2 squared. 4d minus t2 with square root. Okay, this will be 4 pi d t3 minus t2. 4 pi d t2 minus t1. This will be why I'm doing this, because I'm writing this as p x1 t1, and then the two propagators, p x2 t2 given x1 t1 times p x3 t3 given x2. That's why there are three items. Yeah. Okay. This is what I explained to you yesterday. Again. Okay. Okay. Diffusion equation. Someone remembers the diffusion equation or has some idea? Are you familiar with this? You could think it's this, but in reality, there's a diffusion equation for the probability itself. And this, well, often for this example, it is very simple. Usually it's written like this. Like the partial derivative in time is the diffusion coefficient times the second derivative with x to this thing. What does this mean in this context? Is that partial of p x2 t2 1 t1 with respect to t2 is of the time in the future. It's a bit strange with the derivatives backward in time. Okay, remember t2 is greater than t1. This is equal to d, the second derivative with respect to x squared, x2 squared of p x2 given x1. This is the diffusion equation. Often you will see in books that this disappears because they do it for t1 equal to 0 and x equal to 0. This is not t2, this is called t. And this, they do the same here. That's why they write it like this. Okay. This is a key point. The diffusion relates the time derivative, the propagator, with the spatial derivative. So actually you can check yourself, you can take this and verify this equation yourself. This is very easy. You should do it in 3 or 4 lines. It's just algebra. Just to convince that what I'm telling you is correct. Okay? It's so simple. Sometimes there will be some errata in the calculations. so this is the second example. All fine, you understand? Okay, this is just a system that is diffusing in space, and this is the probability, but the trajectories, I gave you another day, this will be x, this will be t. The trajectories will be continuous, and they will be diffusing in space. Okay. Similar to random walk, but it's continuous in time, continuous in space. Right. So the last example I will give you is also, I think, very common in physics. And for this, I think I need less space. If you didn't finish copying, let me know. But it's too late. So there's another example. Quite used in different phenomena in physics. It is the Poisson process. Poisson process. Poisson process is often called point process as well. This following. So this is time. Remember, the Poisson process is when you have an event that can happen with a certain probability. And all the time, you have the same probability for this to happen. So at some point, an event happens. This, in the time axis, I will say the event happens or not. When it happens, I will put a point here. Okay? This means that at T1, there was an event. Then at T2, there's another event. T3, there's an event. And later, T4, there's an event. Here, I'll say that this is a Poisson process with rate R. Rate R is the following. So it means that this is the probability per unit of time for an event to happen. But in every, if you take a window, a time window of length delta t, the probability for an event to happen in between t plus delta t will be always r delta t. Okay, so r has units of 1 over time. It's a rate. So this process, what you can do is to accumulate the number of events that happen. You can sum how many events occur up to now. And this will give you n of t, which will increase when you have a count. So you start from 0, and then you have one event. 1. You continue, there's another event. 2. There's another event, 3. There's another event, 4. This is a stochastic process as well. It is Markovian. It's used in biology, it's used in physics, it's very common. And this
question.
Yes.
This is the thing that I had problems in probability course also. What is that rate?
Rate is a parameter of the process. So here there was one parameter which was d, the diffusion coefficient. The Poisson process has one parameter. It's the r. So I tell you, define a Poisson process. So okay, define a Poisson process. But then I need a parameter. So I can tell you, define a movement in the line, rectilinear movement in the line. What do you need? You need the velocity, no? It's just the only parameter. If I ask you diffusion, what is the parameter of the diffusion? It's the d. If I tell you a bias diffusion, you also need the velocity. 2 parameters. The Poisson process has only one parameter. There's only one thing you can control in the Poisson process. It's how fast things happen.
We have always the things, the events that have equal probability here.
Yeah, sure.
But we don't know when they will happen.
Yeah.
Like a decay of.
exactly a decay of a nuclei. But each nuclei will have a different decay rate. They will decay at different speed, no? So there is one parameter only in the dynamics, which is this R. In the nuclei is lambda. It's called lambda. Okay, this is one of the things. But if I tell you, okay, I think this was in your interview actually. You look at the sky and there's a probability to see one rising star per, I don't know, per half an hour. What is the probability that you see 3 of them in 10 minutes? This is the type of problem you can know. But of course, it would be different at the different days. In summer, it will be much easier, so R will be high, and in winter, it will be low. The latitude and so on. So this would be what controls the dynamics.
So this probability is the probability that if we consider a certain interval of time, we will see one of these events.
Exactly. Exactly. This is the probability for one event to happen. R delta 2. It's good you make me this question because I didn't explain it that good. But this is probability for one event. In the interval T. Okay, this is also called stationary process because no matter which window you look, the probability won't change. Probability for the event to happen. Okay. From this, you can compute very simply, and this is in all probability theory books. What is the probability that n equals n at time t? There were a total of n events in a time t. And this is just, well, you can call it this lambda to the power n. Okay, this is in all the books. N e to the minus lambda. And lambda here is the average number of events in a time t. And what is this? This is nothing but RT. Okay. In this context, lambda is RT. Probability that there are n events at time t is this quantity. So the n appears in this way. There's the parameter is lambda. So remember, this will be a distribution of this type, Poisson. Okay, this will be RT. And if you replace lambda by RT, you get RT to the power n, RT factorial, sorry, n factorial, e to the minus RT. Okay. And maybe that's it. This is the distribution at time t. So this means at time t, what is the probability that I'm here? And the propagator it has the same structure. So P of N2, T2, given N1, T1 has exactly the same structure. It will be R T2 minus T1 to the power N2 minus N1 divided by N2 minus N1 factorial times E minus R T2 minus T1. Okay, this is in its full generality. When you put T1, 0 and N0, is equal to doing this because this is like conditioning. Okay, and it will give you this one. This is what you get when you make T1 equals 0, N1 equals 0, T2 equals T, N2 equals T.
I will found this formula on the power n then over m factorial.
This one?
Yes, and previous.
This is something I can give you as homework. It's very good exercise. But you can think about it, and the next day we can discuss. It is not so difficult. It's not so difficult. It is not so difficult. You can really get it from here. Like. You really get it from here.
We don't understand the question.
How to derive this?
Oh, okay.
Oh, the Poisson distribution.
The distribution. This is
Statistical inference.
this is probability theory lecture 1.
Okay.
I think it's a very good exercise of probability theory. We could do, but I want now to focus on something else. It was not advanced with the physics and not even with biophysics, which is I don't know if I have time. The next class at 3. Or is it 4?
3.
It's at 3. Okay, it's a pity, but I wanted to introduce you to one equation. I don't know if I have some time, but in 3 minutes it will be very, very complicated to go through this. So the next thing I will discuss will be the Chapman-Kolmogorov equation. It's an equation Chapman-Kolmogorov. It's an equation that is obeyed by all Markov process. Then many biological processes are stationary. So, for example, you have an enzyme that is taking a product, reactant, and becoming a product. So this is a non-equilibrium process that is stationary. It's not going anywhere. The enzyme is always there working. So I have to introduce you something of stationary process, and then I can also discuss non-Markovian process a little bit. But as I said, Markovian are much more used in biophysics in general. So it is a big pity I cannot continue because now it was a very interesting question. But if you have any doubts, this is the moment to ask. No? Next week, probably I will bring you the homework of the first block. This, not of this, of the first block. It doesn't mean the homework that I give you, you will have around 1 month to solve it. It's not that you must solve it in the same day. Okay, take your time, think about it. So it's good you have energies to work, but the exercise won't be that difficult in the first round. The second round will be more advanced. Will be with just stochastic clusters. Yeah. Okay, so we finished with this. Today was very short. There was a lot of things I wanted to explain the next week for this.
That's a book reader.
Huh?
Book reader.
This is a tablet, but it's very nice. If I have I'll show you. Huh? No, I don't have my pen, but this I wrote myself, and you can also underline. You can.
You wrote it in that.
Huh?
You wrote it in
I wrote this here.
there.
Yes.
Which brand?
This is called Remarkable. It's
It's Marco.
it's Remarkable.
This company.
My student told me about this last year, and I was very excited when I tried because it really gives the feeling of. And what they say is that it has no internet, no mail, and there's no way to distract yourself. And this is
That's very good. Actually.
nowadays it's very good because with this,
Yes, no.
this is nice. It looks good, but
I think actually
you are burned with the notifications. It's all notifications all the time, and it's maybe you're with the phone. So with the phone you can work. It's great. At least to me.
I was looking for one. I found Sony. It was about $1,000.
Oh, this is much cheaper.
Very expensive, yeah.
This one, I don't know. For me, it was 400, I think. But now there's Model 2, so it will be more expensive. The new model. Yeah, I mean, anything you learn about tablets, let me know because it's useful. But this one I recommend you to use it. It's really, really
It'd be better than carrying all of this.
Yeah,
This-
I had the same problem.
Unfinished page.
I mean, it's like weight training.
Yeah, the only problem I find is that the page is too small, so there you have more space.
Yeah.
The only problem is that because Sony one is a much bigger space and its reaction to your writing is faster.
Ah.
And because of that, it's very expensive.
Yeah, well, probably 1,000 euros should be good.
And however, is still black and white, gray, not color. It's not color.
No, this one is, by now, it's black, gray, and yellow. But yellow you don't see it. You see it later when you pass it to PDF. So,
And it do not bother the eyes.
not much, it doesn't have,
Do not
Light.
reflection.
It's like English.
Yeah, it's like indicated that.
it's like ebook more or less. Yes.
Would you like some cake?
I would appreciate, but I'm diabetic, so I don't think I can. No, maybe I can pick a piece and bring it to my office. So when I get,
It's her birthday.
It's my birthday.
wow,
And they got me.
congratulations. Auguri, they say in Italian. It's auguri when you are, auguri. I'm not Italian, but yeah, well, I'm happy to try. Wow, chocolate cake, wow.
Oh, you have a really nice dish inside.
Yeah, we can use it up there.
We can use it for our kebabs.
Wow.
You can.
Yeah.
You can ask the guy from.
Oh yeah.
Water,
Guy from the sky.
water, water. We need you here. There is a nice chocolate cake.
We are celebrating here and some.
The students want to give Walter a piece for his nice explanation.
No, so they surprised me here. And if everyone was saying happy birthday, made me start the voice.
We said happy birthday from the sky.
They said this today?
Yes.
Really? Wow, this is,
So we should definitely give them some.
this is amazing. Incredible. I think it should be a tradition of all the groups. All the groups should bring a cake.
If I get access to a kitchen, I'll bake for everyone first. If I get access to a kitchen. I just hope I don't break.
Take a picture of it.
Oh.
Don't you want that? Okay.
We could have brought our knives, by the way.
Yeah, I forgot.
I would have
Seaweed.
brought. Not weed. Seaweed.
Okay.
You get it.
Yeah, I didn't get it.
I was talking with one of my friends. He's now in Netherlands, and he was speaking about the stores in Netherlands.
That's
They
because it's
sell
legal.
weed and they're completely
It's
legal,
legal.
and they have no problem with any kind of drugs.
Well, yeah, Netherlands is very special in this in Europe. It's not a place like that. Okay.
Is this
Is this
enough for you
enough?
or?
Or do you want
Sure.
it bigger or smaller?
Well, maybe. I think it's fun. Yeah.
Are you sure?
Very nice.
Enjoy.
Enjoy.
Thank you.
How
And happy
about
birthday.
you? Do you want a big,
Small pieces.
small? Like,
Yeah, because I have a lot of.
Mateo is coming now to teach, no?
yes.
And to eat.
And to
Let's
eat.
eat first.
And
I
to
think
eat.
first
To
we,
eat first.
Let him eat
Thank
first
you.
so that he
I'll try.
Be a good.
Do you have
What is-
I have an extra in my.
Okay.
Basket.
It's very
You want a
good.
big slice or a small?
You should give a piece with your colleagues that are in the